Hello student, welcome to the web optics course. Today we have lecture number 48 and today we will going to do a specific problem where Fresnel diffractions is calculated for a circular aperture. So we have lecture number 48 and in today's lecture we are going to calculate the Fresnel's diffraction for a circular aperture. So let me draw the setup. In the last class we had demonstrated a similar kind of setup, but there the aperture was arbitrary and we figure out a very important parameter, that is the constant. So this is x small y, and here we have the aperture. Okay, so this is the aperture, but this aperture has a specific shape and circular in nature. So some sort of symmetry we can expect from this problem, and then we have screen here and there is a point P over the screen whose coordinate is x, y and z. Coordinate here, z coordinate here is 0. Exactly the same treatment I am going to follow. So if that is the case, we know that my DEP was proportional to E naught divided by R e to the power of I k r. I can also include the omega t term because this is essentially a propagating wave, but in the last calculation we omit that. Even if you put this, there will be no effect, but here for the completeness let us put and dx dy. R we calculated, so R was this z plus x minus small x square divided by 2 of z plus so DEP is essentially, now if I remove this proportionality constant, this proportional sign to make a proportionality constant, and that proportionality constant we calculated in the last class, which was minus of I k divided by 2 pi, an interesting looking term, and then we have E naught. Then executing all these we get exactly the same calculation that we put forward in the last class. Except this omega t term, but does not matter, this even if you put the omit the omega t term here, it will give you the same thing, and over area and then we have e to the power of I then that thing we need to execute. So, this integral, whatever the integral we have is a bit difficult to perform analytically. So, this is the integral. So, to make life simple, what we do, we calculate everything over z axis. That is that is the simplification we can make. So, this integral is not going to calculate because here everything is going to change. So, instead of that, what we do, that we restrict our calculation with the variation of the z. So, that is, this is the point where we have x y is equal to 0, and so if I put a dotted line towards this point. So, here the x y is 0, but z is equal to z. So, this is a z plane. So, we want to calculate over z how, if I move the screen over z, how these things will going to change. So, for the time being we will not going to calculate the entire integral, rather as I mentioned that we can calculate. So, the intensity variation we will look for the intensity variation over z axis. This intensity variation over z axis we want to check first. So, that we can do by making, that means what we are doing is x, putting this coordinate x and y equal to 0, because I am looking only over this z axis. As soon as I do that, my integral become very simple, and I can write that the total E for the point 0, 0, z is essentially I k divided by 2 pi with a negative sign, however. Then E naught, and then we have e to the power of I k z minus omega t over z, and then we have the integral e to the power of I k divided by 2z and small x square plus y square and dx dy. That is the thing we need to execute. Now, for circular symmetry we have a few advantage, and that is this. So, that was the aperture we had. So, over the aperture, the xy point we can write as, so this is my phi and this is my rho. So, x can be simply rho cos phi and y can be simply rho sin phi, such that x square plus y square becomes simply rho square. So, and the area will be rho d rho d phi. So, this area integral will be like this: e to the power of I k divided by 2z, and then rho square, and then we have rho d rho d phi, that is the area. So this I can divide into two parts. One is the integral of phi, which goes 0 to 2 pi, which is d phi, and another integral which we can go 0 to some radius. So if the radius of the circular aperture is a, to 0 to a e to the power of I, then k divided by 2z, and then we have rho square rho d rho that we have. Now this first term is simple, it is simply 2 pi, but this I can simplify by taking, let k rho square divided by 2z as some new variable, say q. So we have k rho divided by z d rho will be dq, such that rho d rho is equal to z by k and dq. So also the limit need to be changed. So when rho tends to 0, q is also tends to 0. When rho tends to a, upper limit, q tends to simply k a square divided by 2 of z. So that is the value we have. Now putting all this together, this integral, area integral e to the power of I k to z rho square rho d rho d phi, that is essentially 2 pi integration of 0 to this value k a square upper limit divided by 2z, and then e to the power of I q, then z by k dq. So this is simply 2 pi divided by k and z, then e to the power of I q divided by I with the limit 0 to k a square divided by 2z. So this is 2 pi divided by ki. Note that this beautiful term again appear here, which is 1 by alpha actually with a negative sign, then z is here, then we have e to the power of I k square by 2 z minus 1. Just put the limit, that is all. So, k square, let us put k square by 2 z is essentially k is 2 pi divided by lambda, and then we have a square divided by 2 z. So, these 2 will cancel out, and essentially we have pi multiplied by a square divided by lambda z, and I write it pi into another variable p, where p is a square divided by lambda z. That is the value of the p. I just put the new variable. Under this new variable, however, this expression, that is the integral of this area, is simply comes out to be this 2 pi divided by I k, then we have z multiplier, then we have e to the power of I pi p minus 1 with the new variable p, and we can manipulate e to the power I p and we get a something. So, let me do that. So, this is 2 pi divided by I k z, and I can take e to the power of I pi p by 2 common, and if I do, then I am going to get e to the power of pi p by 2 minus e to the power of minus I p by 2, which is essentially 2 of I of sine pi p by 2, that we get. So, once we have this integral for this area, so mind it from where we started this calculation, and this calculation was started here. So, this part, this area calculation was we are doing so far. So, E essentially comes out to be this. So, my E over the z axis, that means 0 0 z, this is this minus of I k divided by 2 pi, that is the value we calculated in the last class, that is the value of the alpha proportionality constant. Then we had E naught e to the power of I k z minus omega t propagating wave, and then finally the integral due to this area. So, we have 2 pi divided by I k, and then we have a z here, and then we have 2 of I here, and e to the power of I pi p divided by 2 is also there, and we have a term sine pi p by 2. This is the term we have. Now, intensity, so you can see that 2 pi ik 2 pi will cancel out, 1 minus I will be there, but intensity I at the point z, this is the point we are talking about, 0 0 z, is proportional to mod of E evaluated as 0 0 z, mod square of that. If that is the case, we have a very interesting looking expression, and that is I is equal to some constant I naught, and all this term which is having I will cancel out, and essentially we have sine square here we have divided by z term, because that is important. Let me go back and check it, because I should have yeah, here we have divided by z. So then these z actually whatever is there will cancel out, and then if I take a mod sign, so everything will go away except this sine square pi by 2 p term. Mind it, where p is equivalent to a square divided by lambda z, that we replace. We replace this term. Let me check. Yeah, p is a square divided by lambda z. So that term. So here, if I plot this, we are going to get an interesting kind of plot, and how the intensity will going to change over z point. That is, I am plotting now I, which is a function of z only, divided by I naught. I make it normalize. So this is the value of 1, which is the highest value of sine. So the variation of the intensity, if I plot as a function of 1 by p, because 1 by p corresponds to z lambda with some scaling. So that is equivalent to lambda divided by a square and z. So that means by making these aperture same, lambda a square is constant, and I am moving this point. So what I am getting, the intensity distribution has a curve like this. It is a different curve to plot actually. Gradually these periods will going to change. It will be something like this. So the variation of the intensity over this. Now what is the meaning of that? Let me go back and check. So what we are doing, that this is the aperture, this is the aperture which is having a circular structure, and here we are placing the point P, and now we are changing this point. This problem, however, we have already discussed qualitatively when we are discussing about the Fresnel's zone. So, what we are doing when we are changing this point P, this whatever the value was there, the distance r naught, if you remember with this notation r naught, then these zones, the area of the zones were depending on r naught. And what happened that if I move towards this aperture or move away from this aperture, what happened that these zones will going to change, and because of that we will going to get a circular, a bright, a maxima, a minima, a maxima, minima, this kind of result for different points. If I move say here, for this point maybe we have more. So, if the aperture, so the zone area, for example, the radius was radius of the zone, if you remember, it was root over of n pi and n r0, sorry, n r0 lambda, that was the value. Now, if I change my r0 every time, then the number of zones, the area of the zones also going to change, and if it changes, then we have sometimes a odd number of zones and sometimes we have even number of zones depending on which point we are talking about. Suppose this is P1, this is P2, etc. We move towards the aperture or away from this aperture. So, based on that, what we are getting, that different zones will be exposed, and in this case we can get maxima, minima, alternatively this kind of points. Exactly a similar result, at least qualitatively, we derive today, where when we plot Iz, that is intensity over this is my z axis divided by I naught over 1 by P, which is proportional to z actually. So, this is actually lambda z by a square. We are getting a result which corresponds to a similar feeling. So, we have a maxima, then minima, then maxima and minima over this distance. So, that means this is the distance over which we are moving, and alternatively maxima and minima we are getting. So, this result is very nicely, whatever the result. So, I do not have much time to discuss more, maybe in the next class I will do. So, what I try to show in today's class, that by doing a rigorous calculation based on the Fresnel's law or the Fresnel's expression, that is finding the intensity by doing the integral, we come across a similar qualitative result that already discussed in this particular class when we are discussing Fresnel's zones. So, zones is a different concept where we divide a particular waveguide, particular wavefront to we divide this particular wavefront to different zones and allow the wavefront to propagate. Then essentially from a given point we are looking those zones, all odd and even zones are adding up. So, if there are odd even zones together, then we find that the intensity go minima, and we calculate that qualitatively. In today's class, what we find is exactly whatever the concept we have for zones, a similar kind of things one can calculate by doing the integral thing. However, we do not do the integral for entire region, only we are considering what is happening over the z axis, and we find a very concrete result showing a similar kind of structure. With that note, I would like to conclude. So, in the next class we will do more, we will calculate few more things related to that. Thank you very much for attention and see you in the next class.